A small piece of uranium about the size of a grape has the power to generate enough energy to light up an entire neighborhood for a year. That might sound almost unbelievable at first, but it sparks the question, how can something so small contain such enormous power? The journey of enriched uranium is not just a story of science, it's a story of history, engineering, discovery, and the shaping of the modern world. To understand it fully, let's take a deep look at how this rare and dangerous metal is mined, processed, transformed, and finally used to power cities across the globe. The story begins in the late 19th century, when uranium wasn't considered particularly special. It was in 1896 when French physicist Henri Becquerel made an astonishing observation. Uranium emitted invisible rays all on its own, without sunlight or any external source. This was the birth of radioactivity as a concept. His work inspired Marie and Pierre Curie, who dedicated their lives to studying these strange emissions and discovered entirely new elements like radium and polonium. Just a few decades later, in 1932, James Chadwick identified the neutron, a subatomic particle that would prove critical to unlocking nuclear energy. Then in 1938, Otto Hahn and Fritz Strassmann, with vital input from Lisa Meitner and Otto Frisch, demonstrated something that seemed almost like science fiction. A uranium atom could split in two when struck by a neutron, releasing a burst of energy far greater than anything seen before. This process became known as nuclear fission, and from that point forward, uranium was no longer just another mineral. It became the key to an entirely new form of energy. But there was a complication. Natural uranium mostly contains uranium-238, about 99.3% of it in fact, which does not easily undergo fission. Only a tiny fraction, around 0.7%, is uranium-235, the isotope that makes nuclear energy possible. To make uranium practical for reactors or weapons, the amount of uranium-235 must be increased. This process is called enrichment, and it quickly became one of the greatest scientific and technical challenges of the 20th century. During the Manhattan Project in World War II, scientists pioneered the first methods. They tried gaseous diffusion, which forced uranium gas through thin membranes so that lighter isotopes could be separated, and electromagnetic separation, which bent ionized particles through magnetic fields to pull apart isotopes. These worked, but they were slow and devoured enormous amounts of energy. In the 1950s, a breakthrough came with the invention of the gas centrifuge, a machine capable of spinning uranium gas at staggering speeds and separating isotopes with far greater efficiency. These devices became so critical that their blueprints were guarded like national treasures, considered state secrets by governments around the world. What made enrichment such a turning point was that it shifted uranium from being just a scientific curiosity into a practical source of controlled power. The ability to enrich uranium-235 meant that reactors could be designed with predictable outputs instead of unstable reactions. It also allowed governments to unlock the enormous destructive power of nuclear weapons, changing global politics forever. The very idea that spinning cylinders of metal, invisible to the public eye, could determine the balance of power between nations gave enrichment a near mythical aura. Engineers working on these systems often describe the centrifuges as temperamental giants capable of incredible precision but unforgiving if mishandled. Even a small technical flaw could bring an entire cascade of machines to a halt, yet when operating smoothly, they represented one of humanity's greatest engineering achievements, blending chemistry, physics, and high-strength materials into a single system. This was the point where uranium became not just an element of the Earth, but a cornerstone of the atomic age. In 1951, the potential of enriched uranium was put to the test when the experimental breeder Reactor 1 in Idaho lit up 4 small light bulbs, the first electricity ever produced from atomic energy. Just 3 years later, in 1954, the Obninsk power plant in the Soviet Union became the first station to connect nuclear power to the electrical grid using uranium enriched to around 5%. This was the dawn of civilian nuclear energy. Today, enriched uranium provides about 10% of the world's electricity, a remarkable achievement that shapes the lives of billions. But how exactly does uranium move from being a rock buried deep underground to becoming the polished fuel that powers reactors? The journey begins in some of the most remote landscapes on Earth: vast deserts in Australia, open plains in Kazakhstan, and rocky terrains in Canada supply about 70% of the world's uranium. Here, the element is locked inside minerals like uraninite, often called pitchblende. These ores may only contain uranium in concentrations as low as 0.1%, sometimes up to 2%, but that small fraction is enough to fuel nations. To extract it, massive excavators carve away layers of earth in open-pit mines, exposing the rock for processing. In other regions, miners tunnel deep underground, sometimes hundreds of meters below the surface, to follow uranium-rich veins. There is also an innovative method called in situ leaching, where chemical solutions such as sulfuric acid or carbonates are injected into the ground to dissolve uranium directly from the deposits. The dissolved uranium is then pumped back to the surface, sparing the need to dig giant pits or tunnels. No matter the method, once uranium is extracted, it must be transported to processing facilities for the next stage. At these plants, the ore is crushed until it resembles coarse sand, a texture that allows chemical treatments to separate uranium from the other minerals it is mixed with. The crushed ore is then placed into large steel tanks and mixed with strong acids or alkalis that leach out the uranium. What emerges from this complex process is a bright yellow powder called yellowcake, or uranium oxide. Despite its harmless appearance, this powder contains about 80% pure uranium. It has a faint metallic smell, and while its radioactivity is relatively low, it is still dangerous to breathe in. So workers wear protective suits, masks, and use specialized ventilation systems. To give a sense of scale, 1 ton of yellowcake can produce the same amount of energy as several million tons of coal. It is at this stage that uranium truly starts to reveal its extraordinary energy potential. From the processing plants, yellowcake is sent to conversion facilities. Here, it is transformed into a chemical compound called uranium hexafluoride, often abbreviated as UF6. This compound is especially important because it can switch between solid, liquid, and gaseous states at relatively low temperatures, which makes it perfect for the enrichment process. Conversion begins with purification, removing impurities like sulfur, magnesium, or other trace metals. The purified uranium is then exposed to hydrofluoric acid in sealed reactors, producing uranium hexafluoride gas. At room temperature, it can solidify into crystals that technicians sometimes call nuclear snow because of its pale greenish appearance. It's a compound that requires extreme care as it reacts violently with water to form toxic substances. For this reason, conversion plants are equipped with corrosion-resistant equipment, advanced ventilation, and sensors that can detect even the smallest leaks. Now comes the most critical step of all: enrichment. Uranium hexafluoride gas is fed into tall cylindrical machines called gas centrifuges. These centrifuges are technological marvels made of ultra-strong alloys and carbon composites. They spin at over 50,000 revolutions per minute inside vacuum chambers that reduce friction. As the gas spins, centrifugal force pushes the heavier uranium-238 isotopes outward while the slightly lighter uranium-235 collects closer to the center. This separation process is delicate, and even the tiniest imbalance, just a few milligrams of weight, can damage the centrifuges. To prevent this, each one is monitored by seismic sensors and real-time control systems that adjust their speed with incredible precision. A single centrifuge can process tons of uranium hexafluoride in a year. But enrichment facilities don't just use one machine. They use cascades, hundreds or even thousands of centrifuges connected together, each one making the uranium a little bit richer in U-235. These cascades often fill entire buildings and run non-stop for decades, producing uranium enriched up to around 5% for commercial reactors. The enriched uranium gas is then converted back into a solid form. Through carefully controlled chemical reactions, it is turned into uranium oxide powder once again. This powder is pressed into small, dense pellets, each one about the size of a fingertip. Despite their tiny size, these pellets are powerful. One of them contains as much potential energy as a ton of coal. To make them reactor-ready, they are baked in furnaces heated to around 1,400 degrees Celsius, forming tough ceramic materials that can withstand the intense heat and radiation inside a nuclear reactor. The pellets undergo strict quality control. X-rays scan for microscopic cracks, laser scanners measure dimensions to micrometer precision, and spectrometers check for impurities that could interfere with nuclear reactions. Once approved, the pellets are stacked inside long tubes made of zirconium, a silvery metal that resists heat and corrosion while allowing neutrons to pass through. Each tube or fuel rod contains around 400 pellets stacked precisely. Robots handle this process inside clean chambers to avoid contamination. Finally, dozens of fuel rods are bundled into fuel assemblies, carefully welded and tested until they meet exacting standards. These assemblies weigh around half a ton each, and just one of them can power 100 homes for an entire year. When the assemblies reach a nuclear power plant, they are placed inside the reactor core. A single reactor might hold nearly 500 of these assemblies, totaling thousands of fuel rods. Here, the magic of nuclear energy truly begins. Inside the core, uranium-235 atoms split apart when struck by neutrons, releasing tremendous amounts of heat and more neutrons that sustain a chain reaction. The energy released by splitting just one uranium atom is millions of times greater than burning a single carbon atom in coal. To keep the reaction under control, control rods made of materials like boron or cadmium can be lowered into the core. These rods absorb neutrons and act like brakes, slowing or stopping the reaction when needed. The entire system is surrounded by reinforced concrete walls, some as thick as 2 meters, designed to withstand natural disasters or even direct impacts. Inside, automated systems monitor temperature, pressure, and neutron activity constantly, ready to shut everything down if the slightest irregularity is detected. The heat generated from fission doesn't just sit in the core. It is used to boil water, creating steam under high pressure. This steam is channeled into massive turbines that spin at nearly 1,800 revolutions per minute. The turbines are connected to giant generators, which transform the mechanical motion into electricity. A single reactor can produce more than 750 megawatts of power, enough to supply 500,000 homes with electricity. Unlike coal plants, which spew smoke and ash, nuclear reactors emit almost no carbon dioxide while operating, making them one of the cleanest large-scale energy sources available today. Make sure to give the video a like, share it with someone who loves science and technology, and subscribe for more content like this. What are your thoughts on the role of nuclear energy in the future? Leave a comment below, and let's continue the conversation.